So now we're ready to start with part B, and in part B we see that we are starting to add some of the base. So let's refresh your memory on the reaction, which I have written here. Here is the weak acid, and we're going to start adding that strong base and having this reaction take place. If we look at where we are on the graph from our introductory video, you see where point B is? We're rising a little bit, but we haven't risen a whole lot from the pH of where we started on the previous problem. Now, when we do this problem with 10 milliliters, what we realize is when you're doing this one-way reaction, we don't go to equilibrium. We don't do an ICE table, and you'll see this presented in a couple of ways, but here's how I like to do it. I like to do it with an ICF table instead of an ICE table. It has a very similar feel to our ICE table, but it's going to go to completion. So this is final after the whole reaction has taken place. This is a way of doing a limiting reactant problem. And so what we're going to do is we're going to put moles into this table and not molarity like we did in our ICE table. So I need to know the moles of these reactants that get placed in there. So I read off of the table and we'll get the values in there. For the moles of HA, okay, that's my weak acid. I have the molarity given to me, which is 0.249. And I remember that molarity is moles per liters, okay? So if I took and multiplied by how many liters I had of this acid, which is 20 milliliters, or 0.02, how many zeros do I need? I need 3 zeros after that, okay? That's how many liters of the acid got added to that solution. And when you multiply those together, you get 0.00498. And that's the moles of the HA. Okay, so now we can plug that piece of information into the table, 0.00498. Now we're going to need moles of OH minus. Well, that's the same as the moles of the NaOH because there's one OH in every NaOH. So I'm going to take the molarity times the volume of the sodium hydroxide. It tells me it's the same molarity, 0.249 moles per liter of the sodium hydroxide. But we're taking 10 milliliters of this solution instead of the 20 that we had up here. So there's 10 milliliters converted to liters, and that is going to give me a value of 0.00249. And I can plug that in under the hydroxide. Now, before this reaction takes place, we don't have any of that, and we don't care about the water. There's a large excess of that. Now, what do we do in an ICF table? This reaction will go until it goes completely to products. It's a one-way arrow. So we look here and see which one's the smaller value. It's this one. So this can react until I consume all of the smaller one and leave me with nothing. Now the change line is just like in the ICE table. It is the reaction taking place. So I look up here and I see it's 1, well, right here, 1 to 1. So I know I would have to react 0.00249 here, and I would have to produce 249, okay? So I'm producing on this side. When I subtract these two, I have 0.00249. And when I add these, I have 0.00249. So now I've got my F line. I examine my F line and say, what do I have here? Well, I have a weak acid, and I have its conjugate base present in solution. A weak acid and its conjugate base is a buffer, and buffers get to use the Henderson-Hasselbalch equation. pH equals pKa plus the log of the concentration of the base over the concentration of the acid. Now, what we know is they're both in the same solution, they have the same volume. We can replace the concentrations with the moles of the base over the moles of the acid. And now we can start plugging some values in. pH equals pKa, which is the negative log of the Ka. They told me the Ka value is 1.54 times 10 to the minus 5. We take the negative log of that plus the log, and we look for the number of moles of base. Well, this is the acid, this is the base. The number of moles is 0.00249. The number of moles of the acid is this number, 0.00249. Well, the log of 1 is 0, so all of that is going away. The log of 1 is 0, and that gives me the pH equal to pKa, and the value is 4.812. Now, before we leave this, let's talk about where we are in our titration. This is called halfway to the equivalence point, okay? When you're halfway to, now do you agree with that? I would need equal amounts. I would need this much to be at my equivalence point of the base. When I keep on adding until I get to this number, that would be by definition the equivalence point. This is half that number. So I'm halfway to the equivalence point. Whenever you're halfway to the equivalence point, this number and this number are going to be the same. Pause and ponder that and make sure that that sinks in. I'll say it again. Anytime you're halfway to the equivalence point, this number and this number have to be the same. So anytime you're at the equivalence point, you're going to have a log of 1, which is 0. And your pH is going to always equal the pKa value. pH equals pKa. So that's worth writing down. At halfway to the equivalence point of a titration, well, you get the picture. I don't think I've spelled it right. A titration of a weak acid with a strong base. It's a quick way to know the Ka value of that weak acid, because at that point, if you could measure the pH, it would equal the pKa. So if you were in a laboratory and you stuck a probe down in there and you noticed that you were halfway to the equivalence point and you said, well, what's the pH? Then you suddenly know the pKa value because you know the pH. They go hand in hand right there. And this is a handy thing to know. I wouldn't say it's handy to memorize, but it should make sense to you that if you're halfway to the equivalence point, that these have to be equal to each other, and that would make this term go away and make that statement true. So now, what have we done? Let's look at our picture here. If we're halfway to the equivalence point, we are at point B. The equivalence point was 20. We're halfway to the equivalence point at 10. And if you were to read over on this graph over to this spot, you would have the value at which pH is equal to pKa, and you would know the Ka value. You could get the Ka value of that weak acid.